So what happens when that 2 hours?
Okay, we should probably get started. Right. Okay. A couple minutes past the time. All right, so welcome back. It's week 5 now, I believe. Okay. You know, I'm still waiting on this. There's supposed to be a microphone coming for me to use so that I can, use the speakers in here so I don't have to yell so much, but I'm not sure where that is, so for now I still don't have it. And, it's kind of funny. Remember on day 1, this cable wasn't here, and somehow, miraculously, every day since then it's been here. I don't know why. It was there before classes started and ever since, but okay. So I think I sent out an email that I posted PA2. So PA2, which is listed here, is now available, I believe. So you can click on it. Okay, it's about binary trees and arithmetic expressions. And this link should work as well. All right. And, it's just like the other ones. Download this and fill out, do the exercises. And it's due this Saturday at 11:59. All right. And the reading for this week is PAPL 15 and 16. So 15 is it's just about testing, like the little check blocks or the where blocks that we've been looking at. This will kind of give you a little more understanding of how that stuff works. And of course, there's stuff like this that you can ignore. Or just read what's there, okay? It's relevant. But the really important chapter for this week is chapter 16, which is about higher order functions, or functions as data. That kind of means the same thing. So we'll start looking today at what exactly are higher order functions, and what do they look like in Pirate. Okay, and then after I introduce a little bit of stuff, then we might come back and look at this a little bit in class, because I know from last year, I think this stuff was confusing to students. Okay, there's a little bit of calculus stuff. It's really not that big of a deal. So I might come back to this. Okay, and well, I would like to prepare us. I would like to prepare you to be able to get started on the homework. So I also, I realized I haven't looked at binary trees at all in class. Okay, so I think we can do that as well. It's kind of the natural next step for us. We've seen, natural numbers and lists, and then the next thing is binary trees, where it's sort of like a list, sort of like a linked list, but instead of only one child, there are 2. Okay. Right, but before we get to that, there are a couple other things that I would like to show you. Okay. One of them was we were trying before to come up with lists where the elements had different types, right? Because at least if you're using the type checker in Pirate, then you're kind of restricted in the elements that you can store in lists. They all have to have the same type. And so, you know, we found some kind of hacky ways of getting around that, but you don't want to do that. Okay, but I can show you, using things that we've seen so far, that it's actually possible to, you know, within the rules of the type system, you can still store elements of different types in the same list in a more principled way that you know, encodes your intent of what you're doing in the type system more accurately. Okay, so let's take a look. And whoops, let's make a thing. I don't know what to call it. There's already a list file, so we can use this. Okay, so we can do it using some types. Okay, and I showed you this either type at some point, if you recall, where it had two type parameters, and there were two constructors as well for the either type, and we called it them left and right. So I'd say, okay, there's, you know, it's either a left of type A or a right with a type B. Okay, and maybe I should use a different file here so that it compiles more quickly. I'll call it list2.r. Oops. 2. Okay. All right, well, so it turns out this type is already defined for us in the standard library. So let's take a look. Pirate either. Okay, there's one of these things here is either. And if you look, it's exactly the same thing that I just wrote down. All right, because it's a pretty common data type for, you know, a choice between two different types. So of course, you could use this. You could have a list of type either. Okay, so let's take a look. Suppose I want to define a list called L1, and I want it to contain, say, both strings and numbers. Okay, so what I'll do is say either string or number as the element type of the list. Okay, so it's a list of either string or number. And how will I define it? Well, if you just write, say, you know, hello, a string, and then some number like this, it's not going to work right away. Okay, what does it say? Well, type checking failed because of a type inconsistency, and it complains about string not being the same as number. And why is it doing that? Well, it's not even getting to our type annotation that we wrote down. It's just looking at this list expression, you know, list hello 124, and just from trying to type check that in isolation, it's saying, geez, these don't match up, because we still have this constraint that all the elements of a list have to have the same type. Okay? So the way to fix it, of course, is to make them have the same type by injecting them into the either type. So now they'll have the same type. They'll both be elements of either string number. All right? So it's a rather straightforward thing to do. We use the left constructor for a string and the right constructor for the number. And now it'll work. Now it'll work. Now, oh, we have a list of elements of different types, but we've been more explicit about what their types could be. All right, and so you could do this with a more complicated data type as well. You can make your own data type with however many constructors you want, with whatever, you know, values of whatever types go into those constructors, and then that would allow you to have a list of that type. And so, you know, it's actually quite flexible. Okay? And so there really is no problem. There was also a question at one point about what if, so it had nothing to do with lists, it was just about return values of functions. And it was like, well, do you always have to return the same type? And, well, the same kind of thing applies. If you want to have the option to return values of different types from a function, then you could just use the either type. So I could have a function, I'll just call f because I'm being lazy. And who knows what it does? Number takes a number maybe, and then I can make the return type an either type. So either number or Boolean. Who knows what I want it to be? Okay. But then again, it's the same thing, where I just have to return a value of type either number Boolean. So I can do something like maybe if the number is negative, if x is 0, then I want to return the number. Say I just return x in that case. Of course, if you're looking closely, you'll see that this isn't quite right. But else, if it's not negative, then we'll return a Boolean. Then maybe who knows what you would do, but I'll just say true. Okay, let's try to type check. And there's a type error. Again, it's complaining it's a type inconsistency. Because, well, it says we have this type constraint, either number Boolean, and it's incompatible with number at line 11, column 4, which is where, that's right here. So it's saying, oh, this is a number, and I expected an either number Boolean. So what's the solution? How do you turn a number into an either number Boolean? You use the left constructor. And we'll have the same issue here. And there you go. Okay, so I just wanted to show you that. All right?
Yeah, but does that mean that if it's returned, you can't use that x for the function that accepts a number?
Yeah, you're right about that, because you don't know. So let's say we have another function, g, that also takes a number. And who cares what it returns for now? Okay, and maybe it'll say, if y is greater than 0, it returns true. Let's see if this type checks. Okay, so g, it expects a number argument, and it will evaluate to true if the number is not negative. So now what you're saying is, what if we call f, maybe we want it to be negative, so that it'll be a little more interesting. We call f passing it a number, and then try to thread the result through, to g. Could you do this? Let's see what it says. Well, we get a type error. Type inconsistency. It says that the type constraint number was incompatible with type constraint either number Boolean. Right. So what this is saying is that, of course, what's happening is that g expects a number, and you're giving it something of either number Boolean, which is not the same thing. So you can't do this. And if you think about it, it wouldn't be safe to do this in general, because f doesn't always return a number. It could return a Boolean. So then what would g do with a Boolean? Okay, you would have to you have to be more explicit. If you wanted to be able to do this, then you can either make g also accept an either number Boolean, so then it could take the result of f as its argument, because the types would match. Or you could do some other stuff like, say, you handle the cases. You say, well, let's do the call to f like this. Or how do you do it? Either. And then if it's a left of a number, then you can call g with that number. Otherwise, you have to do something else. And this will type check. Okay? So, the type system, it prevents it kind of rules out bad things from happening, because, if it let you do that thing that we tried to do, Pirate can't tell from looking at this, even though we can tell, well, if you call f with a negative number, it'll always be a number. But because this is a very simple computation, but in general, you could have sort of arbitrarily complicated things going on inside of f, with some, it might even diverge. It could be an infinite loop, or who knows what would happen. And so Pirate can't, in general, look at code and be able to tell stuff like that this would always be a number when you pass it a negative argument. No, we can tell that here. But yeah, so the type system, you need to fit all the types together. That's all. Okay. We've got plenty of time. All right, so we've seen lists of either, or list of sums, I could say. That's a useful thing. And so, there's also a list of products, which is also useful. Okay, you could have lists of pairs of elements. And when you start working with lists of pairs, then there are a couple of functions there's one in particular, I guess it's a pair of functions, that you may have seen already somewhere, maybe not, called zip. Zip and unzip. Okay, sometimes they have other names, but those are kind of the standard names. So I suppose I could show you zip and unzip just because they're relevant here. And they show up a lot in functional programming. Okay, so I'm going to write this zip function. Okay, I'll call it zip. And I'll make it polymorphic in 2 types, as 2 type parameters. And what it's going to do is take a list of A as one of its arguments and a list of B as the other argument. So it takes 2 lists, and it doesn't care what their element types are. And it's going to zip them together so that the result is a list of pairs where, you've just kind of, it's called zip for a reason. You're zipping them together. Let's take a look. So I'll say L1 has type list of A, and L2 has type list of B. And the result type, I'll put it down here, is list of. Okay, and then we need a pair type. And I just realized that, I have mentioned this before. So Pirate has the either type in the standard library. So it's not really built in, but it's provided for you. But Pirate actually has products built into the language, and there's special syntax. Okay, so like what we were calling before, pair AB, which we could implement if we wanted to. Well, Pirate already has a thing for that, and it looks like this, where you use curly braces. Maybe I'll move it over a little. Use curly braces and semicolon to separate the types. Okay, so this is going to be this is a pair type or a product type of 2 types A and B. And you can have more than 2 as well. So, you can do this, and so now it's a 3 tuple. All right. So what type am I going to use? I'll do this. A, B. So this will be a list of pairs of A and B. Okay. Let's verify. Oh, it doesn't work. Oh, it doesn't like the fact that I'm reusing this name L1 because I used it up here. It's a semicolon, which is kind of weird, but that's how it is. Okay, so this type checks so far. So, it understands what this means. So let's go ahead and write it. So there's kind of a decision you have to make. It's very straightforward when both of the lists have the same length, right? Because then they line up perfectly. But what about when one of them is longer than the other? And so what we're going to do in that case, and what is not always the choice that's made, but usually is that you'll just stop whenever one of them runs out of elements. So we're going to be kind of traversing these lists in parallel, pairing their elements together. But then as soon as you run out of one of them, then you're done. So the length of the result will be equal to the length of the shorter of the 2 lists. Okay. So let's do this. I'm not going to spend a lot of time on this. I just want to show you though. Okay. So let's do cases on L1. Okay. So like I said, when you run out on either end, on either side, then you're done. Okay. But here, I'm just choosing names here. I'm going to call the element here X, and and the rest will be x's. Okay? In this case, we'll do case analysis on L2. If it's empty, again, the whole result is empty. But so now we're in the case where both L1 and L2 were non-empty lists that look like, link x's and link yy's. And so now, in this case, we can do something. What will we do? Well, we form the pair of x and y as the data element, and then we will recursively construct the rest of the list. Okay, x's, y's. Okay. So, this is a useful function. And there's a corresponding function that's sort of like the inverse, which you would call unzip. That will take a list of, like this, a list of pairs, and unzip it, and give you actually a pair of lists. So I'm not going to write that. That would be a good exercise for you to do. I'll go ahead and I'll write the type of the function. So it takes a single list of pairs. Let me move this up. It should be called unzip. And it will give you a pair of lists. Okay. So, if you're bored at home, you can go and try to implement this. It's not very hard. All right. What time is it? Okay. So that's all I want to show you for that stuff. And now let's get to binary trees. Okay. Binary trees. So you've probably seen binary trees somewhere already. So it's just a tree where each node in the tree is either a leaf node, it's either a terminal node, you call it a leaf, or it's an internal node or a non-terminal node that has two children, exactly two children. So here's some example. I'll draw some. Okay, like maybe we have a binary tree of numbers. Okay, so like the simplest case would be a single number. Okay, I guess I could draw like a circle. So this would be when the tree is just one leaf. Okay, but then suppose you have a more interesting tree that's like, maybe it has two leaves. Oops. And the root of the tree is now, not a leaf, and it has two children. Okay, and so this is a recursive data structure, and it could, these trees could be very big. All right, so we can see how to encode these binary trees in Pirate. All right, with a data type. So I'll call it btree, and we will make it polymorphic in the type of its elements. And so there are different ways to encode binary trees. The way that we'll do it here is that, sometimes you have data elements at the internal nodes, but that's not what we're going to do. We'll just say the leaves contain the data elements, and the nodes just have children, but don't contain any data elements. So all the elements are at the leaves. Okay, that's what we're going to do. So if we have a B tree of A, it could be a leaf with an element of type A. Okay, that's one case. And the other is that it could be a node. And what's that, a node? Well, there's no data element, but it has two children. And the children are themselves binary trees. So I'll just say L for left should be a B tree of A, and R should also be a B tree of A. And there we go. So it's rather straightforward encoding of binary trees as a Pirate data type. Okay, and so we can do all sorts of programming with this type. You can implement all of your favorite algorithms on binary trees. And so some of the stuff that you'll be doing in PA2 is with this type. All right? And so we can look at some examples of functions on binary trees. So we can do some programming with binary trees, and it's, it feels a lot like programming with lists, because of course they're very similar to lists. They're sort of a generalization of lists, or yeah.
Did we say here that a node has no data?
That's right. So yeah, you could encode this differently. So and sometimes you'll see something like, where a leaf actually doesn't have any data, and then the node has the data and the two children. Oops. Right, this is another thing that you can do, but that's not what we're going to do. Yeah?
I'm curious how you would encode an empty binary tree. Because it seems like you have to have either a leaf with an element, or you have to have a node with two leaves or two subtrees that they'll eventually have to have an element somewhere.
Yeah, so with this encoding up here, there is no empty binary tree.
Okay.
Yep. Oh, but yeah, you could have the empty binary tree with this other encoding, just be a leaf, right? That's true.
How do you traverse
We'll get to it. We'll do some of that, okay? So let's write a function that, how about this? Let's write a function that sort of like flattens a tree, okay? So it'll take a tree where, the tree contains some elements, and it will produce a list of elements that are just the elements of the tree, okay? So I'll call it tree elements, okay? And it's polymorphic, and it will take a B tree of A, that I'll call T, and produce a list of A. Okay, so far so good. So let's try to do this. Okay, and you'll find that it's pretty straightforward. Actually, it's a lot like the programming that we've already done. So how are we going to do it? Well, let's do case analysis on the tree. Let's do cases on T. Because, well, you can always do that with these data types. And we need to handle the two constructors. So what we do in the leaf case, when we have a leaf and there's an element inside, how do you turn a leaf tree into a list? Sure. Just create the singleton list, that contains that element. Okay. So that's the leaf case. It's very straightforward. That's the base case. But then in the node case, where we have the left and right children, okay. So L and R now here are B trees. B tree of A. Okay. Well, the very same reasoning that we were using before when programming with nats and with programming with lists, it still applies here. And the key idea is that you can do recursion on the subterms. Remember, there's this thing called structural recursion where, well, it's safe to do the recursive call on structurally smaller parts of the input. And here, L and R, since they're children of T, they're smaller parts. You can do a recursive call on L, and you can do the recursive call on R. And you have a similar kind of induction hypothesis where you sort of assume that the recursive call does the right thing, that it's correct. Okay, so we can do this on L, okay, that we have that to work with. So tree LM's L, by the induction hypothesis, is the list of elements from the left subtree, from the left child. Okay, and we also have, you know, the same thing on the right. And so the recursive calls, what they give us, these are the lists for the two subtrees, for the two children. And so what do? Well, given two lists, how do we create a list out of them? Well, we could use our append function, right, that we defined. But of course, now that we've done that, we can kind of start using the actual standard library function. So I think there's a method here that we could use. Okay, so you can just take the left and then append the right on the right. Now let's see. Well, it type checks, so that's a good sign. Okay. So, you know, it's a pretty straightforward function here.
So is this printing top to bottom or in order, post order, or what?
Well, it should be, I believe it's, well, all the elements are at the leaves instead of at the nodes. So, but it should be like left to right, you know. We could experiment, I suppose, by writing a test case.
I mean, if it's a normal binary tree
Well, so these aren't binary search trees necessarily. So we don't have any guarantees yet on like the ordering of the elements. In fact, we don't even know if there is such a thing as ordering the elements of type A. A is just some type. Who knows what it is? We don't necessarily have an order relation defined on A, right? But if this was number, then you have sort of the natural ordering on numbers, and then you can start imposing additional conditions on the tree, like, oh, the elements should appear in the tree in order with respect to that ordering. And we'll get to some of that as well. But for now, there's really, this is like the most basic setup where we don't know any of that yet. But let's take a look. Let's create one. Well, so we're going to call tree_lems on a tree. And, well, so the easiest case that is non-trivial will be a node with 2 leaf children. And I'll just say, put numbers in there. So Pirate will see those numbers and say, oh, okay, you're using B-tree of number. Okay, so that's what A will be instantiated with number, and that gets propagated through to tree_lems. It says, oh, you're using tree_lems at type number. Okay, but so this should be, I would think, list 2, 3, right? Let's see. Yep, looks good. And this is the sort of thing that you might be interested in actually proving instead of only checking a few cases. And if we have time, I might show you an example of a proof like that. But you know, just like before, how like with nats and lists, how you have this kind of inductive reasoning. So that should suggest to you that there's a similar kind of induction proof principle for binary trees, where you know you've got the base case, and then you've got the inductive case, where you have not one induction hypothesis, but 2, right? You get to assume the induction hypothesis for L and for R, right?
Currently, you're appending the left tree to the right tree.
Yeah.
How are you appending the left tree to itself?
I'm not sure what you mean.
I mean, you're appending the elements from the left tree from the right tree to the leftmost element, because you're going to stop recursion from there, and then you're going to start recursion at the right tree, right? So you're going to go to the upmost left, I guess, to the left if you can, then you're going to go to the right, correctly, right?
Well, let's take a look at this append method, because you know we're using the standard library append. Let's see if I can find it. See what they say. So, well, we don't see the code for it, but I suppose it should work just like ours did. But But the idea is it produces a new list with all the elements of the current list, which was, for us, that was, that's the list that you're calling the method on, okay? So this is like the current list, tree lms L, followed by all the elements of the other list. And I guess they don't say here, but it should preserve the ordering of the elements as well.
I mean, I know that there's more than one element in the left tree. The elements of the left tree are not appended to each other. You're appending only the last element of the left tree to the right tree. Correct.
That's not what we're doing. That's where your mistake is. We're calling tree LMs on the left tree. And so what does tree LMs of the left tree give you? It gives you the list of all of the elements of the left subtree. So you've got the entire list of all the elements there by your induction hypothesis, because that's what this function does. That's when we're writing this function, that's our intent. We're saying, okay, this function is going to compute all of the elements of the input tree. And that's what we do in the base case, so that's good. And then in the inductive case, we can assume that that's what it does on the two subtrees, and then as long as we can then guarantee that we can take those results and do what the function is supposed to do for the whole tree T, then we're good. Meaning, if you can compute all of the elements of L and all the elements of R, then we can append them together and you'll have all of the elements of T. So that's how it goes. Okay. Now what time is it? Okay. Well, so I wanted to say a little bit more about binary trees, but I need to move on a little bit to higher order functions just to introduce what they are. Okay. So I'll make a new file called function.r. Okay. So what I'll do to start is I'll just show you an example of a higher order function. It's a very small example, okay? Very simple. I'll call it twice. Twice. And I suppose I don't need to make it polymorphic. Okay? So what is twice going to do? Twice is going to take a function as its argument. A function from number to number. Okay? So some kind of function that's defined on numbers will be the argument to twice. Okay? And then it will also take a number, and the idea is that it will just apply this function to the number twice, 2 times. So here, I'll write it down. So we'll take a function f, and here's where we'll see something new. This is the type of f. Okay? Like I said, f should be a function from number to number. Okay, so this is what that looks like in Pirate. We use this arrow type thing, okay, where that is the type of functions from number to number, or functions that take a number as an argument and produce a number as the result. Okay, and then we'll take a number also, and the idea is that we just want to apply this function to n twice. So we'll apply it once, and then take the result from that and feed it into f again. So
any function. That's not a specific function.
right,
Any function from number to number.
any function that has this type.
Okay.
Okay, so this works so far, so it's okay with this. Okay, and so let's say this should apply f to n twice. And by apply, what do I mean by applying a function? It just means calling the function. Okay, that's function application. It means calling the function. Yeah, you apply a function to its arguments. It's like calling the function with the arguments. Okay, so to apply it once, well, you would just say f apply to n. Okay? And then I want to take the result from doing that and apply f again. And that's it. So this is a very straightforward function. But it's twice is a higher order function because it takes another function as its argument. Okay? So let me check that this type checks. Right? And it should type check just fine because, well, f takes a number and we're feeding it n, which is a number. And then the result of f of n also is number, so we can feed it back into f again. Yeah?
So, are you missing the return type for this?
Oh yeah, I left it out. Sorry about that. I guess Pirate was able to infer what it was. Yeah, okay. Yeah.
Why didn't we have to use the lambda notation that I saw in the textbook here? Can you tell me when would we use that? Why didn't we have to use it here?
Okay, we'll get to that next. Because now, so we've defined this function, but now suppose that we want to use it, right? So there are a couple ways, right? You need to be able to pass it a function as an argument. So first, the first way that you would think of doing this is to have a function that you're going to use. I'll call it g, or maybe I'll call it add1. Okay? So what this should be is a function from number to number. So that's what we'll do. We'll make it take a number argument, produce a number result, and I'll make it just add 1. Okay? So now here is a function that we could use with twice. So now I could say print twice add 1, just referring to add 1 by name, sort of pretending that it's like any other value. Okay, and then I'll give it 2. Okay, so what this should do, what we would expect this to do, is to apply add 1 to 2, and then apply add 1 to the result of that. So we would expect to see 4 in the output, and that's what we see right here. So there's no new line, but there's the 4. So that's one thing that you can do, is that you can refer to named functions by name whenever you want to, pass them into a higher order function. Okay, but sometimes that's kind of a pain. You don't want to have to introduce a name for every little function that you use because it starts to become common to use little function, sort of like little throwaway functions that you don't really care to mess up. Well, you would make a mess if you had to introduce a named function for every little thing. And so this is where lambdas come in. Okay? They're sometimes called anonymous functions, because the idea, it's a function without a name. Like I don't want to have to bother registering it with the system with some particular name. Okay? So let's try doing the same thing. And we'll have to put something here. We have to put something here. Right, it just complains because it's trying to evaluate the placeholder. Okay, and so that's where you can use the lambda notation. It's just a notation for defining a function sort of on the fly without having to give it a name. Right? And so in Pirate, it looks like this. You say lam, and then in parentheses, you put the arguments to the lambda. So we'll just have 1 here. And you can, it's common to leave out the type annotations in lambdas just to make it more concise. But I believe you can do that if you want. Okay, and then a colon. And then you have the body followed by end. So the idea is that there's just some expression that goes here. It's just like defining any other function, really, where the body of the function is an expression. So what will we put for the body? N plus 1. Okay? So this should do the same thing. This is a way for us to call twice, passing in this function as an argument, which is the function that adds 1 to its argument, and then 2. So we should end up seeing 4 here again. And there it is. Okay? And yeah, it is common to leave out the type annotations for lambdas. Okay? So, even though it's a requirement for us, I've told you should always have type annotations for your named functions, because it kind of serves as documentation. But for little things like this, you don't have to do that. Okay? So that's where lambdas come in. And they're very useful. And so a lambda can have more than one argument. And I think you just separate them by commas. Of course, this is not going to work if I do this, because let's see what it said. Let's see, what's the type error? Okay. The type error kind of is the opposite of what I would expect. But essentially, it's saying that there's a mismatch here between a function with 2 arguments and a function with 1 argument. Because twice expects a function with 1 argument of a single number, and you're passing in a function with 2 arguments. And that's a type mismatch. Okay? Types have to line up. Okay. Right, so we are running out of time. So we'll pick this back up. I have more to say about higher order functions, of course. And we can also start looking at chapter 16. I think in class I might want to do that. But you should probably be able to get started on the homework. Okay? I think we've covered enough that you can make some progress. All right? So now, yeah?
This might be like a stupid question, but I was wondering, with like all the types that we used so far, we've done case analysis on it. Is there any kind of case analysis on the functions as arguments?
That's a very good question, actually. No. You cannot do cases on a function. Okay? And yeah, that's actually a very interesting question. But the short answer is no. Okay? So, functions are sort of like, this function argument is going to be kind of opaque. It's like a black box. You can't see inside. Okay. Let's see if we have a quiz. You've been very lucky so far. We're about due for a quiz, aren't we? All right. See you Wednesday.